Hi, and welcome to Sustainably Smart Talks. I'm your host, AJ Makarapa, and today I'm joined by my guest, Dr. Saeed Masabi, an expert in electromechanical engineering. Well, that's a mouthful. Well, Dr. Masabi, would you like to explain to us what electromechanical engineering is?
Hello, everybody. Thank you, Ajay, for the very lovely introduction. So, electromechanical systems it's like a very wide area of, like it's a marriage between electrical and mechanical elements. So, specifically, what I do, I work with these things called energy harvesters, and the idea is you replace batteries in very small sensors that are located remotely for gathering essential information in structures or moving parts. This enables longevity of the sensors beyond the lifetime of the batteries by acquiring energy from the environment.
Yes, indeed. Well, that's a wonderful thing because I work in ambient backscatter communications where we're actually trying to work with harvesting energy from the air to make communication possible. And so there's a little bit of intersection between my field and his field. But other than that, we know that Dr. Masabi is a global talent. Tell us how you became a global talent, how you acquired the prestigious visa that everyone is seeking for, the global talent visa.
Thank you. It has been a very pre-planned and quite a nervous journey to get here.
Mm-hmm.
Yeah, so the Global Talent Visa, there's a few categories. The one I'm in is a peer review category. So the way it works is you get an endorsement from like a governing body, and there's a few that exists for technology. The one I chose was Royal Academy of Engineering.
Okay.
And for academics, there's like I think two subcategories in the peer review. The one that I went to is called the Exceptional Promise.
Exceptional Promise.
Yeah, the one where they look at your potential to contribute to the UK in your field.
Okay.
The way I developed my portfolio was through my academic publications and my industrial collaborations to get to like a convincing stage that the endorsing body can, be convinced that okay, this guy can, deliver in the next few years.
Well, sounds good. Sounds very strategic. You said this is pre-planned. So walk us through your journey. Now that you have your PhD, you're working as a postdoc. Where did the roots come from you to become an electrical mechanical engineer?
The roots go back quite a bit. I think, obviously, like if you go back to my childhood, I was a comic book nerd.
Okay.
Really enjoyed the technical gurus like Iron Man, for example.
Yes, indeed.
So which sort of motivated me, if you will, to pursue the A levels in physics, chemistry, further mathematics.
Sounds good.
And then I did an undergrad in electrical engineering. And what I think, I did struggle a bit with the structured layout where I couldn't find the independence to sort of focus on things that I really enjoyed.
Mm-hmm.
And I was still figuring out which part of the engineering fields that I like more and which ones aren't as, attractive to me. So I figured out that sustainability makes sense. Renewable energy was quite like a hot topic back then.
Okay.
So with my undergrad degree, I pursued a MSc in renewable energy systems.
Okay, where did you do your electrical engineering degree and your MSc?
So my undergrad was in University of Hull.
Okay.
So that's where I started after my A levels in Manchester. Then with that, my MSc was in University of Leeds. So the MSc focused mostly on sort of control systems that sort of generate energy and then sort of how to store them, how to transmit them from one place to another. And mostly to do with like wind turbine generators and photovoltaic systems. And with the knowledge that I acquired from that, I realized the potential in the structures themselves and how energy can be sort of accumulated in like a much smaller scale.
Okay.
Instead of like kilovolts and megawatts.
Yes, indeed.
Yeah,
and now you're doing a PhD.
So that's how I transitioned to my PhD, which focused on like same renewable energy generators, but like a much smaller scale, where with big energy systems, you assume that the energy is abundant. So sun always comes up, the wind is always there in the offshore grids, but in like much smaller scale, that's when the challenges become more apparent. Like you have to focus on ambient energy, like there are places where the sun doesn't always shine.
Yes, I agree with that.
Places where there's not much wind going on. So I found that quite interesting, and looking into the mechanics of it and how we can use like inertial generators to take the best advantage of like a broadband range of vibration that exists in systems is what I transitioned into. So hence the term, like, electromechanical systems makes
Yes,
most sort
indeed.
of fitting in my.
Yes, so you're looking mainly at vibration energy.
Yeah,
Vibration. So I know that as a piezoelectricity.
Right.
So application of your research, how would you say, which fields does it apply? Give us a real world life example of your research.
I can give some examples through some of the projects that I've collaborated in recently. So one of the things I worked with was with the National Nuclear Laboratory, and they had like a urgent need of digitalization in their energy storage infrastructures. And primarily, I think the application that I looked at was ventilation systems.
Okay.
So I think the ventilation system that they had was very enclosed areas where it was desired to find unmanned ways of monitoring the steel and the other parts that make up the tunnels. And by employing power autonomous systems in there, where energy harvesters would accumulate energy from the ambient airflow.
Yes.
And then the energy acquired would be used for both for communication and for sensing the critical parameters, such as vibration, chemicals that present in the atmosphere, corrosion as well, being one of the key aspects. That's what I think that the goal was. That's what they really desired, and with my sort of collaboration with them, we made it possible through our sort of electromechanical approach.
Yes, indeed. Sounds like quite exciting. So, but part of your global talent visa expects you to be innovating in your field. So, what does the future look like for you, Dr. Masabi?
What does the future look like for me? That's a very...
Because you're a very strategic man. Everything over is a pre-plan. I would assume you had a good strategy. I'm trying to learn from my peers, my mentors that have done doing exceptionally well. So he's an exceptional promise. Global talent, indeed, he is.
That's very kind. That's a very nice way of putting it. Of course, there's been aspects of the journey where it was. I think it was partially when I knew I wanted to get to this position, but it was through guidance of various academic and industrial mentors, even like peers like yourselves that I met throughout the journey, who sort of gave their experiences, their outlooks at life, and that also helped. But again, the question was what I envision and how I want to. So where I see at the end of the journey. I guess the immediate next step for me is to, at least the way I see it, what I envision now, is to become an academic, a tenured position.
Yes, indeed.
Ideally in Loughborough University.
Okay.
As a lecturer.
Yes, indeed.
More research focused. I do enjoy teaching, but I think sort of pioneering research is quite exciting for me.
Yes,
and going that direction is...
Explain the differences because of what research, what it really means to be a researcher. I'm doing a PhD, but being a postdoc, that means he has graduated, he has his PhDs, he's done, and now he's doing further into that. What does that entail day to day as a postdoc, as a researcher? What does that mean? Walk us through that process, the journey, the life of a researcher.
That's a very, very good question. I think I can explain through my journey. During my PhD, I think independence, it was the beginning of our independent journey, right? So you have a set goal, that this is the plot. So you know what the topic is, you know what the challenges are. So we dig out some scopes, we dig out some novelty. So these are the areas we need to work on. And then we try to turn it into a few chapters. Okay. Ideally, that's the PhD journey. Some people are lucky enough to have industrial partners in their PhD, where the focus is more directed towards the immediate industrial needs, but the outcome I think it's like broader. So you can still come up with solutions that approach to a broader audience in sort of a very specific goal. I think for me, the next step that I pursued was a postdoctorate with industry. It was like an industrial project. One of them was with this thing called the Avatar EU project, where they work on digitalization of transformative air vehicles.
Yes, indeed.
So with that, my task was very specific. I had to install a energy harvester in one of their vertical tail units to transmit wireless data. So the transition from doing a PhD, where I chose, okay, these are the three sectors I want to work on, for example, wind turbines, electric vehicles, and human motion, right, to harness energy from, and just to show that, okay, I can power stuff. From that, when I did my postdoc, I realized, okay, now I have a set goal. So I can't just generalize my solutions by sort of estimating these are the inputs and this is what the output could look like.
Yes, indeed, yeah, I agree.
I'm given very specific sort of constructs to stay within. and if it works, and it has to work within their specification, otherwise, it's a concern.
I agree with that.
So that was my postdoc, and my current role, which is a Vice Chancellor Independent Research Fellow.
Yes, indeed.
The independent being the key term. That's what they emphasize on in the job description. And I think in this position, the transition from sort of being guided to a point where you only do what's told, compared to having the freedom to choose what's important, to justify to the audience, being the interview, the people who interview and the people who give the funding, to justify the importance of something I see potential in, and to pursue that for the number of years that I have the position for.
Yes, indeed.
So that's so I think I think it's all has the same theme, from a PhD to postdoc to research fellow, and hopefully to like a more sort of permanent position as well. But yeah, so I think for each sort of category that independence and the goals vary. Yeah.
So you moved from what, the PhD, you're more dependent on your supervisor?
Yeah, I think although we don't really rely on them for specific technical details, we rely on them for which direction to go to. So, for example, they can tell us, okay, because it's like it's motivated by funding.
Yes, I agree with that.
Yeah. So, whereas later on in life, so at the stage I'm now, it's a bit more sort of, it's more of a burden on myself that if I choose a direction that doesn't lead anywhere,
okay,
I'll be left alone after 2 years or however long the fellowship lasts.
Okay.
But yeah, so I think with time you have the benefit of having confidence in
yes, indeed,
the areas that you find more interesting.
As part of the fellowship, what are your requirements or obligations to the university?
I think so. The fellowship, the VC fellowship, I think the main goal is to acquire an externally funded fellowship. So earlier we were having a discussion. You mentioned one of our the other
yes.
I think one of the interviews that you had earlier.
Today, yeah.
Yeah.
I did.
To plug to the previous episode.
Yes, indeed.
Was about
episode 10.
Yes, watch it. So that was about, I think, the RANG fellowship. Yes. Yeah. So that's an example of an externally funded fellowship.
And that's specifically the Royal Academy
of Engineering.
Yes.
Very prestigious. Yes.
Very accomplishment. Please go on.
So that's one of the examples of an externally funded fellowship. So these are money from the government or the sort of these funding bodies that people like ourselves bring to the university. That most of which we use for our own research to sort of enhance the quality of research and the outputs that the university provides.
Yes, indeed.
It also like sort of supports the university in other ways, like building the roads, funding the cleaning, facilities, management, etc. Yeah. So that's like my ultimate goal. But to get there, I think I've also been. So I also promised a few dissemination activities, going to conferences, for example, sort of seminars that I organize myself, stuff like this. Interesting podcasts where we expose ourselves to the broader audience.
I agree with that.
People get to know who we are. Yeah. Okay. So dissemination, publication, of course. I think one of the common themes in academics, wherever you go, is willingness and this dire need to publish.
Yes, I agree with that. Publish. I'm on my third conference paper that I'm trying to publish at the moment. I've written one accepted, one a best presentation for that one in China last year.
That's very interesting.
Second one I've published, it's in line of publishing. Hopefully that next time I come with more results about that one. It should be in Brazil at the end of the year. Other ones are under review, and I look at more people who publish works who made many works that during their career, how I can aspire to I think my supervisor, Professor Lambert Tharan, for that. Talk about your publications now. Your publications, how many have you had? What's your process of writing papers, the review process to have really good papers, especially compare the weighting of a conference paper and a journal paper?
So publications, how I envision it and what's my process. Okay. I think I've been quite lucky with my journey. So on average, I try to publish one conference paper and one journal paper every year. If I don't, I feel like I'm sort of falling behind on track.
It's a very hard target, to be honest. It's a very hard target, But you have high aspirations, definitely.
And I think, having said that, like every researcher have their own sort of very sort of private and unique way of approaching this. And publication is on the end goal. The end goal is to do high quality research, right, for everyone. And fortunately, in my field, I think because the way energy harvesters work, like it's very tailored to different applications. For example, if I wanted to do self-powered sensing in this room where there's barely any energy, if I found a way to do it, then that would be like a very bold contribution, and that'd be very easy to publish because no one else has done stuff like that. Hypothetically, I'm sure people have, but
Okay.
Fortunately, and the fields I choose there's enough work to be done that it's relatively easy to publish.
Yes, indeed.
I mean, without offending the fellow researchers and energy harvesters who are publishing. I think one conference paper a year and one journal a year is a good target to. I haven't done that throughout my career, but
it's just
that's the
difficult.
ideal
Trust me,
target.
it's difficult. I've been aiming for basically a conference here, conference here, conference here, conference here. Some places don't even require you to have conferences to get your PhD, but Loughborough University is a prestigious university. The reason why it's the sixth best university in the United Kingdom is that we try to have expectations to have our papers to be 4-star, 5-star, RFQ for research excellency framework that we have over here. The REF program that we have over here. I did want to ask Saeed, since you talk about energy harvesting and your conference paper and your research, are you more simulation based or are you more practical based?
I think it's like the way I approach my my innovations, if you will, it's like a spiral modeling. So I have an idea first. Sometimes I work in parallel. So I just build a prototype to see how it performs, and then make a model out of that using differential equations. Sometimes just so basically analytical modeling is my usual method of going. So build a prototype, do some modeling, try to validate the answers, and then do some more exploration with the model to see what are the limits, how it can be enhanced, how it can be optimized.
Okay.
And then sometimes just remake the prototype into like a much more refined version.
Yes, indeed. I like how you put it, the spiral model between the theory into the simulation, into the practical base. Mm-hmm. But what would you say for PhD students working on theoretical simulations throughout and no practical base? How would you tell them to keep on motivated, to keep on seeing the bigger picture? As that what I've seen so far with some students that are working with all simulation based, they tend to run out of steam because they don't see the physical manifestation of what they're working. And I see the ones that are working with practical based, if the equipment is all working, say maybe like I've seen people work in chemistry, say that maybe the machines weren't clean that day, can literally put your results apart, or maybe the building has no electricity that day. If there's no power in one building, I can go take my laptop and go work somewhere else. My PhD is all simulation based. What would you say for either candidate that's working now, solely simulation, solely practical? What would you have advice for them to keep on having a long-term vision? That advice to keep on being motivated, the inspiration, Saeed.
You've asked me a question which I don't have an answer to myself. I struggle with both. I think I do a bit of both. So sometimes I rely on simulation, for example, for CFD analysis, for my system that rely on like aerodynamics. Yes. Sometimes I do like structural analysis using modeling in console or whatever. And prototyping wise, I think like anything that requires testing in dynamic conditions like vibrations or like wind tunnel testing, then that's when I rely on the sort of the lab environments. Now both have their own challenges, as you
yes, indeed, they
very
do.
Nicely put. So with the labs, you are bounded by the 9-to-5 routine.
Yes, indeed.
Because you need technicians, you need your risk assessment, and you need your fire safety and yada yada yada. And you can't really work from home. You can't really work from wherever you want.
No, you can't.
You don't have the luxury to do that. It's like sometimes we feel like manual laborers, back pain and then standing for 4 or 5 hours a day.
Okay.
We become standing pods for different setup because it's easier sometimes than to have tripods.
Okay.
So I think that's the challenge there. Whereas with simulations, not always, but oftentimes you can just remote desktop into it. And I think. While they both have their own challenge and they do have their own sort of advantage, and again, I think one of the keys I found to stay stimulated and to stay motivated in these environments is to try and find collaborative ways of doing research. If we rely purely on simulation, find someone not necessarily in your research group, could be somewhere else, could be different universities. Contact them, network. We go to conferences, find people who are working in your similar stuff, but in a different sort of landscape.
Okay.
If you do simulation for, I don't know, like structural dynamics, find someone who does practical work on it. go and visit them. Go to the lab, they come to you, and then that way we get to not only visualize how it can look like in the sort of real realm, but also how also how people approach things differently and find ways to
yes, because it is a collaborative approach. In fact, it's giving me a few ideas about how I can take my research forward, because I do love the innovations that I've been working, novelty I've created, but
yes.
It all seems beautiful, all in theory, that, oh yes, my method should be 70% better than the what's existing.
Yes.
But until I have tangible results to prove it and actual expertise. But luckily I've been able to speak to professors such as here at the University of Loughborough, Dr. Bansal. They've given me some guidance on which equipment to buy so I can keep on testing that. But then now that you've said that, I'm going to actually follow that up more. Actually, I'll point out to this episode if anything ever comes out, the inspiration that came out for building the ambient backscatter system I'm proposing to make. I'll say it came from this episode specifically. So it does help to have these conversations. That's also why we started this platform, Sustainably Smart, so we can spark conversations that can bring out big ideas. So your research mainly is in energy harvesting. How does that feed into this sustainable model that we're trying to achieve in the world? How does it feed into net zero, reducing carbon footprint? Does your research do that?
I think the way I see it, so again, the key phrase being power autonomous sensing.
Yes, autonomous sensing.
How I try to stitch into sustainability is that some of the system that I target or intend to sort of make smart or more autonomous involve net zero applications. For example, gas transport, clean energy, like wind turbine, so for example, or nuclear, both exist in that kind of realm. Anything that targets the EU 2050 carbon neutrality goal, for example, right? So I think digitalization of these systems make them more sustainable. They can last longer. They can perform better.
I agree with that.
They can reduce dangerous human intervention, for example. And by making the sensors that are used for health monitoring of these kind of setup, making them wireless and self-powered, sort of makes things easier. Helps us, evolve to the next phase. And that's how indirectly I sort of aim to contribute to the sustainability goals of our world.
Yes, I think you are, definitely, because energy harvesting is a really important thing, because I worked actually characterizing 6 renewable energy sources for Internet of Things. I used a harvester board working with Professor Mitchell at University College London. In fact, he's the one who gave me
Paul Mitchell. Paul Mitchell.
At UCL. So he gave me a couple of ideas about what to do, and without him, honestly, I do appreciate everything. Shout out to you, by the way. That did help a lot. So I had to categorize 6 sources. One of them was photovoltaic, which is solar.
Yes.
The heat, so that's thermal. Vibration, so piezoelectricity. Magnetic. So you can get with magnetic induction, so you can power from that's using laws from Tesla's. That's how we get so many innovations with magnetic induction, of course. And then the 5th one was radio frequency harvesting. That's actually what I'm working at the moment. That's how ambient backscatter communication works. It repurposes ambient presence signals. So there is a lot of security issues with that. So it's a beautiful idea without it making tangible into practice. It will lack a little bit or something. That's also why I need to take that transition into more practical work. But how is your lab day-to-day work? Is it are you supported by a team? Do you lead a team as an independent fellow?
So my role involves, I think, at least the technical side of it. I mainly work with the airplane aspect of it. As I mentioned, the installment of the power autonomous sensor node onto the vertical tail unit of an aircraft. That requires collaboration with 16 industrial partners and academic partners, so including Imperial College London, Luxembourg University, DTU, then there's Nippon, so NTT, I think, Nippon, and then there's Evector, the companies that provide the aircrafts. And then there's a few partners from Aero and Auto. Shout out to Dr. Jingjing. And then, so there's a handful of people in that aspect. with the nuclear work that I do, it's mostly people from Sellafield. There's a few people from our university and Wolfson School as well. Then I think lab work mostly involves staying in the tribology lab, where there's some rotating motors and some vibration isolating tables where we can test things that we make. And also in the thermofluids lab, where there's a few wind tunnels to sort of vary the wind speeds to see how our energy harvesting designs can perform with different kind of sensors. And also it's interesting that you mentioned, I'll plug into some technical knowledge now of what sort of energy harvesters are. So you mentioned piezoelectrics. That's one of so there's this thing called transaction method. So with vibration or any mechanical energy, the first step is to capture the energy from the main source to like a secondary source, right? So
yes, indeed.
From mechanical to mechanical. For example, if there's airflow, we convert that into rotational energy using turbines or just bluff bodies to get vibration. If there's a sort of like a rotating shaft, then it's a matter of capturing it into different element. For example, like creating relative speed to transfer the energy into a smaller setting, so we can store it. To do that, we have these things called the transducers. And in vibration energy harvesting, there's 4 to 5 main kinds. There's piezoelectric, that depends on sort of deformation of a surface. And there's like, when a surface deforms, there's potential difference. And if you connect that to a load, then you get like a current. So there's electromagnetic, as you mentioned, where I think it's Faraday's law of induction. So if the magnet passes through a coil or near the vicinity of a coil, the magnetic field changes the current direction and it induces voltage basically. The other two are basically contact-based, where if you have contact separation, you can induce potential difference. That's, I think, electrostatic, or like some triboelectric as well, which relies on, I think, sliding or contact separation as well. So using these as the main sort of approaches, we can convert the mechanical energy into electrical energy. And that's what we then use power electronics to convert to storage, to take into storage units. And these storage units are the small bursts of energy required for the sensors to turn on instantaneously and turn off whenever there is not enough energy. So this is the sort of, I just plugged into the premise of what it is. So yeah, technical work includes sort of looking into all these aspects to making sure there are tailored approaches for each of the projects that we work on. So other than the technical side, I also work on writing research proposals.
Yes, indeed.
So staying up to date with what's required for the upcoming fellowship applications.
Yes, indeed. Yes, indeed. Yes, I want you to continue from there if you can, please.
Publication-wise, I think I want to have at least. I don't want to give numbers. I don't know how many I'll end up doing, but I want to work on at least one by the end of this year. As I think I briefly mentioned about wind tunnels. So ventilation systems is one of the areas I find quite interesting, because most structures in industry, sort of buildings or any services that we rely on, they somehow require ventilation for heating, I stopped at heating as if there's no others, but yeah, so ventilation is something I find quite interesting, and with one of the energy harvesting systems, so self-port sensor nodes I've made, I've done a significant amount of work into refining it for very low input for it to start, harvesting energy.
Okay.
So as low like 3-4 meters per second, it can start.
So how does the system work in terms of like ventilation, heating, and energy harvesting? Trying to get the link on that one.
So I think I'd start with the requirement. So why could we need energy harvesters in a ventilation system? These are quite enclosed systems where we don't often have much idea of what's going on inside, right? So there might be fractures, there might be corrosion, holes, or any like discrepancies in the system, which might either reduce the effectiveness of their primary function, or it might also make it a bit more hazardous. For example, if the ducts are housing just clean air, that just means lower quality environment, sort of air condition in the places that we live in. However, if it's storing or if it's transmitting something a bit more volatile, for example, gases or sort of wasteful fluids, then it's a bit more of an issue if there's fractures. So without going too much into detail about what the specific applications would
let's
be.
leave your patent for. Can we please let me have his patent? Yes,
Yeah, please don't take my idea. It's not very interesting, but it's mine. I'm joking. But yeah, so where it might be hazardous to, I think one of the ways to mitigate for these challenges is to employ sensors in them, right? So sensors that collect the critical informations and then transmit it wirelessly. Wirelessly is important because we don't want wires hanging around in places where
yes, indeed.
they're quite...
Now I'm starting to see as well an intersection between my research
sure.
and your research too.
You work with Professor Will Whittle as well.
Yes, indeed. Yes, indeed.
He does 6G.
I work in 6G too.
Yeah.
Will Whittle works in material surfaces for communication.
Yes,
for this.
sure.
I work on the signal processing bit,
Yes.
so I can see that there's interpolation between our research.
Yes.
But yeah, go on.
So wireless is important, as both of us, I think most people are aware that we don't want wires hanging around.
Yes, indeed.
Yeah. So Bluetooth is nice, radio is nice. So wireless communication is important, and also another aspect is the longevity of these sensors. So with batteries, batteries are a very well developed technology.
Yes, indeed.
However, say if we envision a duct working sort of effortlessly for 20 years,
yes, indeed,
batteries might not be the best solution.
Yes, I agree.
So that's where energy harvesting comes in. So we know that there's a constant supply of ambient energy into the ducts, right? So 3 meters per second, 4 meters per second, sometimes up to 20, 25 airflow going through, right? If you can borrow a minute amount of that airflow to power these sensors, that sort of kind of relieves us from the energy budget, right? So it makes it abundant.
I agree with that.
So that's the scope that I take advantage of with my sort of wind-powered miniaturized energy harvesters.
Okay,
so
that makes sense.
Harvest enough energy to sort of turn the sensors on temporarily, turn them off again, and then turn the BLE module on, so it transmits, so advertises the data, and then have like a localized hub, for example, in where there's enough sockets, like a wireless router or whatever, to then acquire that energy and then do the signal processing, which plugs into your area of expertise.
This is what I work into, signal processing, the other part, but this is all simulation based as well. But the signal processing is mainly always going to be simulation based. That you
then
have
the
that.
added benefit of this is, if we think one sensor can take data from one point.
Okay.
Now, if you have an array of these sensors located in, I keep mentioning duct, but you can imagine any other applications. For example, a big wind farm, where every turbine has like 2 or 3 of these nodes to take data about environment, data about the vibration, data about corrosion, right? And then they cross-communicate bidirectionally between one node to another, right? And then they all send data to the centralized hub. Now we have a vast amount of data from the entire sort of sensing surface that we can use to get more interesting parameters. We can form a digital twin. We can do continuous monitoring for a long number of years, compared to the previous possibility where we had to send humans.
And imagine as well, like one other application use is that it may not be feasible to send humans into some of these areas.
Yeah.
We're having these areas now powered by harvested energy. What we're doing now, we're reducing downtime, reducing human intervention.
Yes.
So extending lifetime capacity. So I can see the beauty of your research and how sustainable it is.
Indeed.
Yes, indeed, how sustainable it is. Well, Said, thank you for sharing your energy and your vision today. Is there any last words you want to share towards the viewers that they to encourage them into adopting more sustainable approaches in any parts of their life, work, research, or industry-related fields that they may be into?
Stay unbiased. Try expose yourself. Read as much as possible, and have a positive approach towards the environment. I think the way I try to see it, leave something behind for the next generation.
Okay.
To enjoy and also continue.
Yes, indeed. Yeah. So part of what I'm leaving behind, the legacy, is part of this podcast. But maybe we can inspire future generations that, that's coming up in front of the camera is not easy, but I'm doing it for the purpose that hopefully we can create a more sustainable future for everyone. I say thank you for coming, sharing your energy, your vision, your passion.
Thank you for having me.
Appreciate
It's been a pleasure.